A train roars past at over 200 kilometers an hour. From the platform, it looks effortless, clean, silent, precise. But in the fraction of a second those wheels are above you, the track is bending under the load, flexing, and very slightly wearing away. Multiply that by every axle of every train, every day, and you have a structure that is constantly trying to destroy itself. Keeping it safe is a hidden, around-the-clock engineering battle. This is how railways actually keep running. Start with what a railway track really is. Engineers don't call it the track. They call it the permanent way, and it's a precisely engineered system of 4 layers. On top, the steel rails. Beneath them, the sleepers, or ties, that clamp the rails exactly 1,435 millimeters apart, the standard gauge used across most of the world. Under the sleepers sits a deep bed of crushed stone called ballast. And below that, the compacted subgrade, the prepared ground itself. Each layer has one job: to take the immense, pinpoint force of a steel wheel and spread it, wider and softer, until it disappears harmlessly into the earth. The unsung hero of that system is the ballast, those rough, sharp-edged stones between the sleepers. They are not just filler. Their jagged faces interlock like a 3-dimensional puzzle, locking the sleepers against the sideways shove of a passing train. They cushion vibration, and the gaps between them let rainwater drain straight through before it can soften the ground. But here's the problem. Under millions of tons of traffic, those sharp edges slowly grind down and round off. The stones stop biting into each other. The track loses its grip on the ground and starts to settle, sink, and creep out of alignment, millimeter by millimeter. Left alone, that misalignment grows until the ride turns rough and, eventually, unsafe. So engineers send in the machines, and the first is extraordinary. It is called a tamper. A vehicle like a placer and tire is essentially a rolling factory. It grips the track, lifts the entire rail and sleeper assembly clear of the ballast, and hauls it back to its exact design position, correcting it both sideways and in height, to within a millimeter. And then it does something genuinely clever. Banks of steel fingers, called tines, plunge down into the ballast on either side of each sleeper and vibrate at a very specific frequency of around 35 Hz. At that frequency, something strange happens. The ballast briefly behaves like a fluid. The stones lose their friction, flow like a thick liquid, and pack tightly into the gap beneath the sleeper. The tines squeeze inward, the vibration stops, and the ballast instantly relocks into a dense, solid bed. Behind the tamper, a dynamic stabilizer then shakes the whole track downward, pre-settling it, so it won't move the moment real trains return at speed. Now turn from the bed to the rail itself. Every wheel that rolls across a rail presses down on a contact patch smaller than a coin, concentrating tons of force into a fingertip of steel. Over time, that relentless stress fatigues the surface of the metal. It breeds networks of tiny surface cracks called head checks, and a rippling where pattern called corrugation, the roughness that makes some trains roar. And here is the genuinely frightening part. A surface crack just 1 millimeter deep, left to grow, can propagate into a complete fracture, a snapped rail, in a matter of weeks. The defense against that is beautifully simple. You grind the problem away. A rail grinding train rolls slowly along the line, pressing dozens of spinning, computer-controlled grinding stones against the railhead. In a shower of sparks, it shaves off just a fraction of a millimeter of fatigued steel, enough to erase every microcrack before it can ever reach the core of the rail. As a bonus, it recuts the rail's ideal profile, so the wheels ride exactly where they should. Now, a detail almost no passenger ever notices, and one of the most elegant ideas in all of engineering. Train wheels are not flat cylinders. They are gently coned, wider on the inside, tapering outward. And a fixed pair of wheels share one solid axle, so they must always spin at the same speed. Watch what happens on a curve. The train drifts slightly toward the outside of the bend, which rolls the wider part of the outer wheel and the narrower part of the inner wheel onto the rails. The outer wheel now travels further per turn than the inner one, which is exactly what a curve demands. The wheel set steers itself perfectly, with no mechanism, no electronics, nothing but its shape. But wheels wear too, and a worn wheel is dangerous. A wheel that locks and skids grinds a flat spot onto its tread. A worn flange goes hollow. Either way, a once smooth wheel becomes a hammer, slamming the rail and the ballast with a violent blow on every single rotation, accelerating damage to everything it touches. The fix is the underfloor wheel lathe, a machine sunk into a pit beneath the depot. The train rolls on top, and the lathe recuts the perfect conical profile straight onto the wheels, without ever jacking up the vehicle or removing a single wheel set. Which raises the real question. How do you find a 1mm flaw hidden somewhere across tens of thousands of kilometers of track? You don't walk it, you scan it, continuously, at speed. Track geometry cars run the network looking like ordinary coaches, but packed with lasers, inertial gyroscopes, and high-speed optical sensors. As they roll, they measure the gauge, the cross level, the twist, and the alignment of the rails, building a sub-millimeter map of the track's exact shape, while moving at full-line speed. Anything drifting out of tolerance is flagged before a human could ever feel it. But the most dangerous flaws can't be seen at all, because they are inside the steel, deep below the surface. So inspection trains go acoustic. They fire pulses of ultrasonic sound straight down into the rail and listen for the echo, because a hidden internal crack reflects that sound back like a flaw in a diamond. Alongside it, eddy current sensors flood the rail's surface with a magnetic field and watch for the tiny disturbances that betray a microscopic crack invisible to the eye. Both run continuously, on a train moving at speed, turning the whole railway into something that can feel its own injuries. Put all of it together, and you get the modern maintenance loop. First, the high-speed scan, geometry, ultrasonic, eddy current, gathering millions of data points. Then automated tree-off. Software flags every defect and ranks it by how dangerous it is and how fast it is growing. Then a repair crew is dispatched to the exact meter of track that needs them, to tamp, to grind, or to replace. And the failure is quietly prevented before it ever happens. This is the shift that changed the railway forever, from reactive, fix it after it breaks, to predictive, find it and replace it before it can. Why pour so much money, machinery, and obsessive precision into all of this? Because the alternative is catastrophe. A rail that fractures under a loaded freight train or a high-speed service can cause a derailment in seconds, with lives at stake. Every tamping pass, every grind, every laser scan and ultrasonic pulse is quietly stacking the odds against that single, unthinkable moment. It is the real, unglamorous reason that railways remain among the safest and most efficient ways ever invented to move people and goods. So the next time a train glides past, and you barely give it a thought, remember the invisible army that earns that silence. The tampers working through the night, the grinding trains throwing sparks, the geometry cars mapping the rails to the millimeter, and the engineers reading that data while the world sleeps. It isn't glamorous, but it is the razor-thin difference between a railway and a disaster. If this changed how you see the tracks, subscribe. There's a whole series on the rails.